Hello everyone, my name is Raul Campillo. This work is entitled Numerical Modeling and Experimental Validation of Step Bonded Joints, and it was a joint collaboration between myself and my colleagues, Rui Machado and Ricardo Rocha. In this slide we can see the main objectives of this work. We will begin by performing experimental tests to step-lap adhesively bonded joints and perform the required data analysis. We are going to evaluate different adhesives and different geometrical conditions, namely the overlap length, and then in the numerical work we will validate the extended finite element method by comparing the obtained numerical predictions with the experimental data. With this purpose, we will evaluate the most suitable damage initiation and damage growth criteria. Regarding the experimental work, the stepped bonded joints were made in an aluminum alloy of high strength, AW6082. We can see in this figure the stress-strain curves obtained experimentally for this material, and also the simplified numerical approximation, and we also have a summary of some of the most important mechanical properties, such as the tensile strength and the tensile yield stress. We considered three adhesives to perform this analysis. The Araldite AV138 is a brittle but strong epoxy adhesive. The Araldite 2015 is an adhesive with intermediate ductility, while the Force it is a highly ductile polyurethane adhesive. We can see the differences between the adhesives, for example, by looking at the last two lines of this table, in which we can see the tensile toughness and the shear toughness with proper values for very brittle adhesives in the AV138 and more ductile behavior in the other two adhesives. The geometry presented in this figure was considered for the step-lap joints. Here we have as the main parameters for the joint LT, the joint length between grips, LO, the overlap length, TP, the adherent thickness, TA, the adhesive thickness, and TA1, the vertical adhesive thickness. As it is possible to see, we are going to make a step-lap joint with 3 steps. And we are going to consider overlap lengths between 12.5 and 50 millimeters. Regarding the experimental procedure, we will begin by the fabrication of the specimens. First, we acquired bars with the final width of the specimens. We have to cut these bars. After that, we machined or milled the steps in a conventional milling machine. In the third figure, we can see the adhesive application. And finally, in the fourth figure, we can see one specimen already curing with pressure grips being applied so that the joint is in proper place for bonding. Regarding the experimental results, in this graphic we can see the maximum load as a function of the overlap length for the 3 adhesives, including the standard deviation. We can see that for the AV138 the maximum load increases only 40% from an overlap length of 12.5 to 25 millimeters. For the 2015 we have a higher improvement of strength because of the ductility of this adhesive, and for the Force 7752 we have also a major improvement in the maximum load as a function of LO. In the table below we can see the percentile improvements between consecutive overlap lengths for each one of the 3 adhesives, and we can see that the maximum increase was obtained for the Force 7752, which acquired improvements of 86%, 46 and 31 between consecutive overlap lengths, and this is because of the fact that this adhesive has a high ductility. Regarding the numerical work, we performed an XFEM analysis. In Abacus, we consider the two-dimensional analysis, considering geometrical nonlinearities, and also we consider the element size grading or bias effects, so that we could have a more optimized mesh. In the tables to the right, we can see the full set of properties that we considered for each one of the three adhesives and for the criteria that we are going to use in the XFEM. We can see here an example of mesh details for a joint with an overlap length of 12.5 millimeters. We can see that we considered only a single row of solid elements to model the adhesive, but with a visible discontinuity between the consecutive vertical and horizontal adhesive layers, and this is because of the physical impossibility to model these corners in this methodology. The mesh size for the adhesive layer was elements with a size of 0.2 millimeters. We can see in this slide the different damage initiation and the damage growth criteria used for the XFEM. Beginning with damage initiation, we considered 6 criteria: the maximum stress criteria, max S, the quadratic stress criteria, quad S, the maximum strain criteria, max A, the quadratic strain criteria, quad A, and also the max PS and max PE criteria, which are based respectively on the principal stresses or principal strains. In which regards to the power law criteria for damage propagation that we consider different exponents, the letter A that we can see in the formula, and we consider exponents between 0.5 and 2. Regarding the numerical results, we present initially the results for the Araldite AV138, in which we compare the experimental results with the 6 different criteria for damage initiation. We can see that the best results were obtained by the quad S and max S criteria, and here for the max S criterion the highest deviation was 13%. For the quad S criteria we had a deviation of only 1% for an overlap length of 12.5, but bigger deviations for the other overlaps. On the other hand, the other criteria did not show to be so suitable, with a maximum deviation, for example, for the maxi and quadi criteria of over 200%. Here we can see the same analysis for the Araldite 2015. Once again, the best results were found for the quad S and max S criteria, but here the quad S criteria gives better results, and the highest deviation for this criteria was 7%, for an overlap length of 12.5 millimeters. For the max S criteria, the maximum error was 28%, and for the other criteria, the results were completely offset of the experimental behavior. Finally, for the SICA 47752, once again, the max S and quad S criteria give the best results, and here for these two criteria we had deviations in terms of maximum value of 7% for the max S and 13% for the quad S criteria, and once again the other criteria, as you can see by the figure, are much offset from the experimental behavior. Regarding the damage growth criteria, we present here the results for the AV138, and we are going to consider both a linear and an exponential damage law with different damage exponents. We can see that the linear softening gives closer results to the experimental maximum loads. Regarding the exponent of 1 presents the best results, with a maximum deviation of 10% for 12.5 millimeters, and a deviation for the exponent of 0.5 was almost 30%, as we can see in the figure. The power law criteria with exponential softening, it was found not to be suited for this case because it highly overestimates the maximum load. The same results for the 2015. Here we can see that the linear damage propagation laws behave almost identically, irrespectively of the exponent, The best results nonetheless were found for an exponent of 1 with a maximum deviation of 7% for an overlap length of 12.5 millimeters, and the maximum deviation for an exponent of 2 was up to 14%, but nonetheless the results are more or less similar. And once again, the exponential criteria showed not to be suited to model this behavior of these adhesives. And finally, for this damage growth study for the SICA 47752, we have virtually identical maximum load predictions between each law shape, either linear or exponential, but once again the linear softening gives much closer results than the exponential softening. But here we had a minor underestimation of the maximum load, which was up to 14% in this case for an exponent of 0.5 and an overlap length of 12.5 millimeter. On the other hand, we had major offsets for the other laws. Regarding the conclusions, experimental, we saw that the maximum load of the step joints highly varies with the geometry and also with the adhesive chosen. We have a higher improvement of the strength with the overlap length for ductile adhesives due to their capability to undergo plasticization, which does not occur for the brittle adhesives. And regarding the XFEM analysis, we saw that this is actually a powerful tool for the strength prediction of adhesive joints if we correctly choose the criteria for both damage initiation and damage propagation. Thank you very much for listening to this presentation.